Hi everyone, this is Huan. I am a PhD student from HKUST. It is my pleasure to introduce our work named DIV, Resolving the Dynamic Issues of Zero-Knowledge Set Membership Proof in the Blockchain. This work is collaborated with Professor Lei Chen. Here is the outline of this talk. We first introduce the background and motivation of this work. Then we discuss the formal definition of the problem we are targeting on. Specifically, we have two optimization problems for both the set elements addition and removal. Thus, we will introduce solutions to both of them. Finally, we discuss our experimental evaluation. To solve the privacy and scalability issues of the blockchain, the technique called zero-knowledge proof has been widely used, which is for a prover to convince a verifier that she or he can correctly compute a witness based on a given input, such that an NP statement can hold. Meanwhile, does not reveal any other information. A typical implementation is called the snark framework, which can be divided into front and back end, where the front end converts the computation of witness correctness check to an arithmetic circuit, and the back end uses ZKP machinery to translate the circuit into the proof generation and verification computations. Notice that the proof verification is usually succinct to compute. However, the proof generation can be costly, which depends on the complexity of the circuit. In this work, we only focus on the front end in order to get more efficient circuit without touching any cryptographic implementation. More specifically, we target on a special ZKP called zero-knowledge set membership proof, which is to prove an element belongs to a set without revealing the element. In blockchain, it is accomplished by three rules. Firstly, a set maintainer set up a set and prepare ZKP-related conversions, then publish the set digest on the blockchain. Here, typical sets, or we call the accumulators, are Merkle tree and RSA accumulator. Meanwhile, elements can be in any format, such as system states or even cryptographic commitment. Secondly, a prover generates the ZKP SM based on a specific set digest. Finally, the verifier verifies the proof and provides services. Notice that the content of the set and its digest can be dynamically updated by the maintainer. ZK-Sync is a typical real application example uses ZK-SM. It implements ZK rollup protocol, which is the layer 2 scalability solution to the Ethereum. Specifically, there is one smart contract in the layer 1 blockchain maintaining the root of account balance state Merkle tree. Transactions are executed in batches to get the updated Merkle root in layer 2, and a ZKP is generated to prove that the state transition is correctly computed. Finally, the update tree root along with the proof are proposed to layer 1, and the contract state can be updated by only one succinct proof verification. Here is the simplified details of the state transition ZKP computations. For each transaction, we need to prove the validity of the sender signature and the state transition correctness, which contains two set membership proofs that both the old and the updated states belong to corresponding sets. There are some other application examples, such as anonymous credentials, where the set represents a collection of authorized users. One need to prove the membership to get some services. We skip the details here. However, the dynamic cases, such as set elements addition, removal, and update, can bring additional issues, which can be viewed from two aspects. The first is the set maintenance cost. Particularly, sets with different cardinalities can have different proof circuits. Merkle tree is an example because its membership proof computation depends on the tree head. Thus, with dynamic changes, costly ZKP resetup may be required. Notice that existing solutions maintain a universal set containing all possible elements to avoid resetup. However, it wastes computation for a sparse set and hard to further scale. For the set update complexity, Merkle tree, for example, with n elements, it takes log n time for any operation. It seems to be efficient enough. However, it is in the crucial path of each transaction execution, which can directly affect the system performance. Finally, to make the updated digest come into effect, it brings the on-chain finalization delay. As we know, due to the non-deterministic property, consensus in public blockchain usually takes time to finalize the update. During this period, any proofs based on stale digest can be invalid. The second aspect is the efficiency issue of the ZK-SM proof generation. That is, with more elements in the set, the circuit tends to be more complex, which has longer proof generation time. Such property is not desired by applications, for example, anonymous credentials, where constant proof time is required. Therefore, the basic idea of DIV is to perform sharding on the set, that is to shard the set into subsets with the same cardinality. The intuition is that there is no difference to declare the membership in the universal set or a subset. By doing so, we can get the following benefits. Firstly, with homogeneous subset, the membership computation check is the same. Therefore, the setup for the ZKSM can only be done once. Secondly, with restricted cardinality, the element update as well as the ZKP cost of each subset can be bounded and not affected by the number of all elements. Thirdly, the operations on different subsets are independent, thus the additional cost, such as on-chain finalization delay, only affects the involved subsets. Meanwhile, the ZKP in different subsets can be computed in parallel. Notice that we should allow one element to be assigned to multiple sets. The reason is that with more choices to declare the membership, it is harder for the attacker to link the proof and the element. However, it brings a security trade-off. That is, the improper element set assignments can expose the element importance information. In particular, for each ZKSM proof, one needs to at least specify which set it is based on. Due to the difference in each element's proof frequency, it will make the usage frequency of each subset different as well, which leaks the element importance information. In this work, we assume that a prover declares an element's membership in each assigned set with equal frequency, because without knowing the proof strategy of other provers. Compared to declaring from a single set, the equal declaring in multiple sets makes the proof with more possible elements, which further decreases the proof element linkability. Then, we provide an example to illustrate our problem. Suppose we have 8 elements with the proof frequency listed in the table. We shard them into 2 sets with cardinality of 5. In the first assignment, element 4 is assigned to both sets. Based on our assumption, the prover will declare its membership in both sets with the frequency to be 1. Thus, based on the declaring frequency of each element, we can compute the usage frequency of each set. Also, we can observe that in the first assignment, adversaries can know that elements in set 1 are more frequently used, while in the optimal assignment, the importance information can be better hidden. Here are some basic concepts and notations to formally define our problems. We abstract the elements and sets without considering their implementations and use E and P to denote each element and its actual proof frequency. Notice that our work does not assume the proof frequency is static. Instead, it is just an estimation result of a period of time. And we use S to denote each set, which is a subset of all elements, with the fixed cardinality K. Then the element set assignment is denoted by a function of E. To control the number of sets, we use delta S to control the ratio of the expected number of sets to the number of elements. That is to say, with n elements, the total capacity of the subset is computed by this formula. Meanwhile, to accommodate at least one copy of all elements, K times delta S must be greater than 1. Then we can compute the set usage frequency of each subset denoted by UI as a summation of assigned elements' proof frequency contributing to this set. Finally, we measure the importance information leak by the entropy of the set usage. We define our first optimization problem aiming to provide a guidance to set maintainers to maintain the subset when adding a batch of new elements to the system. The inputs are a set of existing elements E and their assignments to a collection of set S. The analyzed usage of those sets based on previous transactions, as well as a set of new elements E star, and the set number ratio that has. Notice that in this problem, the maintainers only create new set S star to accommodate new elements without changing the structure of existing sets. Instead, existing elements can be assigned to new sets to reduce the usage frequency of existing sets. We also have 3 constraints to ensure the cardinality of each set, the assignment completeness of new elements, and the unbiased assignment of existing elements. Since our goal is to minimize the information leak computed by the entropy of set usage, it can also be converted to minimize the maximum set usage frequency. Meanwhile, we prove the NP hardness of the problem by reducing it from the load balancing problem. For more details, please refer to the paper. Besides, we also need to consider how to remove a batch of elements from existing set, which is the SMPOR problem. Like the adding problem, the inputs contain a set of existing elements E and their assignments to a collection of sets S, with each set usage frequency. The main difference is that here we have a set of elements to be removed. After deletion, we need to reorganize the remaining elements denoted by ER in the set that previously contained deleted elements. Therefore, we use new sets denoted by SR to accommodate them. Different from the adding problem, the completeness constraint focuses on each element instance in ER. For example, suppose we remove elements 4, 6, and 7. The remaining elements need to be reorganized. And notice that both elements 3 and 5 have two instances to be reassigned. Thus, we need to keep their original distribution proportion in the sets, and instances of the same elements cannot be assigned to the same set. Otherwise, the set usage frequency may change dramatically to cause the information leak. Therefore, the removal problem is harder than the adding. In fact, for both problems, we also consider two situations, which is whether the element pool frequency is known to or hidden from the set maintainer to fulfill different system requirements. For example, in some permission blockchain applications, one may choose to count on the set maintainers and provide the estimated pool frequency to get better service. For instance, in a credential system, the set maintainer is also the authority who can issue or revoke credentials. Thus, in our mechanism, the maintainer should take responsibility for better element set assignments to maintain the credentials. On the other hand, especially in the permissionless chain, the set maintainer may not be the authority who can create or delete the elements. For example, the miners in Zcash cannot create or destroy any commitment arbitrarily, and they can be malicious. Thus, in these settings, provers will not expose their proof frequency, which will not be the input of the assignment algorithms either. For the element addition problem, we first consider the proof frequency is known by the maintainer and design the HFA algorithm. We first create new sets based on the cardinality of E star and delta S. Then, in the first phase, we greedily assign new elements to new sets with unfilled space. After that, we enter the second phase, which is to greedily pick assignable elements from existing sets to fill the remaining space in new sets. The time complexity of this algorithm is linear to the total capacity of new sets, and we prove the approximation ratio of this algorithm is 2. Here is a running example. Suppose we already have 2 sets with 8 assigned elements and their proof frequency contributing to each set. We want to add 6 elements whose estimated proof frequency are listed in the table. According to key and delta S, we need to create 2 new sets. And in phase 1, each time we pick element with the highest proof frequency to assign to the set with minimum current usage to get the result at the bottom. After phase 1, we can observe that the maximum usage still appears in the existing set as 2. Then we enter the second phase. We first compute the table for each element in S2 based on their total proof frequency and the number of assigned sets. The goal is to pick the element with the maximum difference after assigning it to new sets. Here should be element 5. Then we assign 5 to new sets with the minimum current usage, which is S3. After doing so, we observe that the maximum usage appears in new sets, and we stop the algorithm. For the empty space in new sets, we fill them by dummy elements with proof frequency to be 0. With our known proof frequency for addition problem, the only thing we can do is to perform randomized algorithm. Basically, we first equally distribute new elements into new sets. Then we randomly pick elements in existing sets with the maximum usage to fill the remaining space in new sets under a specific probability formula. The intuition is to pick elements that have been assigned to fewer sets with higher probability. We also prove the expected approximation ratio of this algorithm, which conditionally depends on E star and delta S. And in more general cases, the approximation ratio should be 2. For more details, please refer to the paper. Here is a running example. We first compute the expected proof frequency of all elements based on the set usage frequency of existing sets. The result is 9. In the first phase, we equally distribute the new elements and treat each element's proof frequency as 2 times of the expected value to get the usage of new sets. Since the maximum usage appears in S2, we enter the second phase. We first get the pick probability table of each element in S2. Suppose we pick E8 here and assign it to S3. We treat its proof frequency as the expectation value 9. and update the usage of both S2 and 3. Due to the time, we only introduced the basic idea of removing algorithms. We first remove elements from the existing sets and collect all instances of remaining elements in the affected sets. Then we create new sets to accommodate all instances. We still greedily pick elements with the highest proof frequency. The difference is that we only focus on the proof frequency contribution of each instance. Then we assign all instances of these elements to different sets with current minimum usage. For the second phase, we used a similar one as the addition algorithm. Also, we prove the approximation ratio of this algorithm is 2. For the randomized algorithm for unknown frequency, similarly, we first equally distribute every instances of remaining elements to new sets. In this case, we can make sure no duplicated instances from the same elements are assigned to the same set. And in the second phase, we use similar way to randomly pick existing elements to assign to new sets and compute estimated usage for each set. The difference is that every time we pick an element, we need to check if the selected set already has its instance. If so, we need to pick the set with second minimum current usage until we find a suitable set. We also prove the algorithm's expected approximation ratio, and for more details, please refer to the paper. Finally, we introduce our experimental evaluation. The first experiment is to evaluate the effectiveness of our approximation algorithms to protect the importance information of each element. Thus, we use both real dataset, which is the real Ethereum account trading frequency in a period of time, and synthetic datasets to capture the proof frequency on the different distributions. We verify the parameters listed in this table for both addition and removal problems. And we also implement naive random algorithms for both problems on the different situations as the baselines. Our matrices are the maximum set usage frequency as well as the comparison between theoretical lower bound to verify our approximation guarantees. Here we list part of the result, which is to vary the batch size of new elements in the addition problem and the set number ratio in the removal problem in both real and synthetic normal distribution dataset. Results show that the maximum set usage of our algorithms are bounded by 2 times of the theoretical lower bound, which implies that the information leak can be bounded as well. Meanwhile, the algorithms with known frequency can significantly outperform the algorithms with unknown frequency. Therefore, in the settings of reliable set maintainers, our algorithms can well protect the elements. The second evaluation is to evaluate how DIV can help to improve the efficiency of DKSM. Thus, our matrices cover the following 3 aspects. For proof generation efficiency, as we introduced in the background, it is determined by the complexity of the proving circuit. Thus, we use the R1CS constraints count of the circuits to measure it. For proof verification, we directly measure its time cost. For set maintenance, we measure the time cost to prepare a set, including the circuit setup, DKP case generation, and running the elements assignment algorithms. We also measure the time to update elements in a set. We implement DIV on both Merkle tree and RSA accumulators and compare DIV-based and original accumulators on the different cryptographic security level. Results show that DIV-based accumulator can achieve constant time and relatively more efficient ZKP proof generation as well as set maintenance. Finally, we apply DIV on the real application ZK-Think. As we introduced in the background, ZKSM occupies a large number of operations in the transaction processing of ZK-Think. Thus, the efficiency of ZKSM can affect the transaction processing latency of the system, which is also our metric. In terms of implementation, here is the pseudocode of the original circuit of transfer transaction check in ZK-Think. It checks the membership of sender and receiver state in the same Merkle tree. To apply DIV, we first shard the Merkle state tree by restricting the height of account tree of each subset. Then we change the membership check circuit to take 2 inputs of the roots of sub-Merkle trees where sender and receiver belong to. We vary the block chunk size, which is the batch size of the transactions, and measure both the circuit constraint count and the transaction processing latency. Result shows that by decreasing 50% of the total tree height, the system latency can be reduced by 23%. That's all for the presentation. Thanks for listening.